Our universe is hiding colossal secrets just beyond our perception. We are about to embark on a mind-bending journey through 50 galactic phenomena that defy all explanation, challenging the very laws of physics as we know them. You will discover why our entire galaxy is being pulled toward an unseen monster and what strange force is ripping the cosmos apart at the seams. This exploration will fundamentally change how you see the night sky. Are you ready to question everything you thought was real? Our galaxy is not drifting through the void in solitude. It is racing, pulled by an unseen hand toward a destination we cannot see. This is the first great mystery, the Great Attractor, a gravitational anomaly of almost unimaginable power, located some 250 million light-years away in the direction of the Centaurus supercluster. It exerts a force so immense that our entire Milky Way, along with countless other galaxies, is being hauled toward it at a staggering velocity of over 14 million miles per hour. Yet for decades, this cosmic puppet master remained one of astronomy's most profound secrets. The core of the problem lies in its location, positioned directly behind the crowded, dusty plain of our own galaxy. Astronomers call this region the zone of avoidance. It is a blind spot in our cosmic vision, where the dense accumulation of stars, gas, and dust of the Milky Way's central bulge blocks our view of the universe beyond, like trying to peer through a dense, luminous fog. So, what could possibly possess the gravitational might to command entire galaxies? Initial theories suggested it was simply a massive concentration of matter, an immense supercluster of galaxies previously hidden from our sight. But as our observational tools have grown more sophisticated, peering through the obscuring veil with X-ray and radio telescopes, a more complex picture has emerged. The Great Attractor may not be the ultimate source of the pull, but merely a waypoint on a much larger, more terrifying cosmic current. It appears we are being pulled towards something even bigger and more distant, a structure known as the Shapley supercluster. This suggests the Great Attractor itself might be drawn by a force greater still, a chain of cosmic dominance we are only beginning to map. The true nature of the anchor at the end of that chain remains one of the universe's most compelling puzzles. But this immense pull is not the only invisible force at work. An even more pervasive mystery holds our very galaxy together. Picture a spinning cosmic pinwheel like our Milky Way. According to the laws of gravity, stars on the outer edges, moving slower than those near the dense center, should be flung into the void. Yet this is not what astronomer Vera Rubin observed in the 1970s. She found that stars at the galaxy's outer rim were orbiting just as fast as those near the center. It was as if the entire galaxy was embedded within a vast, unseen sphere of something that provided the extra gravity to keep everything from flying apart. This something is what we now call dark matter. It is a substance that does not emit, absorb, or reflect any light, making it completely invisible to every telescope we have. We only know it is there because of its profound gravitational influence. We can see its ghostly hand at work through another cosmic trick, gravitational lensing. The immense mass of dark matter warps the very fabric of space-time around it, bending the path of light from distant galaxies behind it, acting like a colossal, invisible lens in space. This is how we map its distribution, revealing vast, tangled cosmic webs of dark matter upon which the visible universe is built. Despite knowing it makes up roughly 27% of the cosmos, we still have no idea what it actually is. It is the universe's most dominant architect, the hidden scaffolding for every galaxy, and yet it remains utterly, profoundly, and tantalizingly unknown. Yet for all its power, dark matter's gravitational pull is only part of the cosmic story. A far stranger and more dominant force is at work on the grandest stage of all, the expansion of the universe itself. For most of the 20th century, scientists believed that the cosmic expansion born from the Big Bang was gradually slowing down. The collective gravity of all the matter in the cosmos, they reasoned, was acting like a brake, pulling everything back together. Then, in the late 1990s, two independent teams of astronomers made a discovery so shocking it won them the Nobel Prize. They were measuring the distances to extremely far-off supernovae, using these exploding stars as cosmic mile markers to gauge how fast the universe was expanding in the past. To their utter astonishment, they found that the expansion was not slowing down at all. It was speeding up. The universe, against all expectations, was accelerating. Something was overwhelming the pull of gravity, actively pushing galaxies apart. This something is dark energy. Think of it as a kind of anti-gravity, a repulsive force inherent to the fabric of space itself. Unlike dark matter, which pulls things together through gravity, dark energy pushes them apart, and its dominance is staggering. While dark matter makes up about 27% of the cosmos, and all the stars, planets, and galaxies we see constitute less than 5%, dark energy accounts for a colossal 68% of everything in the universe. It is the majority ruler of cosmic destiny. This discovery completely rewrote our understanding of the universe's fate. Instead of a big crunch, a fiery collapse back into a single point, the prevailing theory now points toward a big freeze. As dark energy continues to accelerate the expansion, galaxies will be pulled ever further apart until eventually star formation ceases, existing stars burn out, and the cosmos becomes a cold, dark, and ever more lonely void. Dark energy is the ultimate paradox, a force we cannot see or directly detect, yet it holds the final word on the fate of every single thing that exists. While dark energy dictates the universe's grand fate, far more fleeting signals from the depths of space deliver their own profound mysteries. Arriving without warning, a flash of radio energy brighter than 500 million suns can erupt and vanish in less time than it takes to blink. These are fast radio bursts. For years after their initial discovery, these millisecond-long pulses were complete enigmas, appearing to come from random points across the sky. What cosmic event could possibly release such an immense amount of energy so instantly? We have since traced some of them back to their home galaxies, identifying potential culprits like magnetars. These are the super-dense, spinning corpses of dead stars, possessing magnetic fields so powerful they could strip the data from every credit card on Earth from 500,000 miles away. The eruption from such a starquake could potentially generate a burst we could detect across the cosmos. Yet the mystery only deepens with the repeating fast radio bursts. Unlike the one-off events, these sources fire out multiple bursts, sometimes in frantic, unpredictable patterns. This rules out a single, cataclysmic explosion as the source. It suggests a factory, an engine that can produce these incredible outbursts again and again. Is it a neutron star orbiting a black hole being periodically shredded? Or perhaps some advanced form of cosmic lighthouse, a beacon we simply cannot yet comprehend. The sheer power and brevity of these signals challenge our understanding of physics itself. Decades before we even had a name for fast radio bursts, another singular event captured humanity's imagination. In 1977, a radio telescope at Ohio State University known as the Big Ear was engaged in a quiet, systematic search of the heavens. On August 15th, a narrowband signal, a pure tone, slammed into the receiver. It was so powerful and so perfectly aligned with the natural frequency of hydrogen, the most common element in the universe, that the volunteer astronomer who discovered the printout, Jerry Amon, circled the alphanumeric code and simply wrote "Wow." Next to it, the signal lasted for a full 72 seconds, the exact time it would take for a stationary telescope to pass a fixed point in the sky, and it has never been heard again. Despite numerous dedicated efforts to find a repeat from that same patch of space, the silence has been absolute. It was not a human satellite, not a passing aircraft, and it did not match any known natural celestial source. The WOW signal remains the most compelling and frustrating candidate for a potential transmission from an intelligence beyond our world, a one-word testament to a mystery that has endured for nearly half a century. Even our own cosmic neighborhood holds stars that behave in ways we cannot fully explain. Among them, one star gained worldwide fame for its bizarre flickering, a star known as KIC 8462852 or Tabby star. Data from the Kepler Space Telescope revealed that this star would dim by enormous amounts, sometimes more than 20%, in erratic, unpredictable patterns. This was not the clean, periodic dip of an orbiting planet. It was as if something massive and irregular was passing in front of it, sparking wild speculation about alien megastructures, vast energy collecting arrays built by an advanced civilization. Yet, as fascinating as that idea was, more careful observation has pointed toward natural, if still strange, causes. The leading theory now suggests a vast, swirling cloud of dust and debris, perhaps the remnants of a shattered moon or a gigantic swarm of comets orbiting the star in a tight, chaotic formation. This dust is exceptionally fine, like smoke, which explains the specific way it blocks light. So while we may have ruled out a Dyson sphere, the mystery remains. What cataclysmic event could have created such an immense and intricate dust cloud around a single star? Far beyond any single star, some entire galaxies are sculpted into impossible-looking forms. Gaze upon Hoag's object, a galaxy that appears as a perfect cosmic bullseye. At its heart lies a dense, ancient core of yellow stars, then a vast, seemingly empty gap. And finally, a perfect, separate ring of vibrant blue, newborn stars. It is a structure so symmetrical it looks artificial. How does such a thing exist? It defies our standard models of galaxy formation, where spiral arms typically sprout from a central core. One theory suggests a rare galactic collision, where a smaller galaxy shot straight through the center of a larger one billions of years ago. The gravitational shockwave would have compressed gas in the larger galaxy, triggering a wave of star formation in a perfect circle, much like a pebble dropped in a pond creates ripples. Yet no trace of the intruder galaxy remains, and the pristine nature of the central core makes the event difficult to model. Hoag's object stands as a serene, beautiful, and deeply puzzling exception to the rules. From a perfect ring, we turn to a perfect geometric mystery much closer to home. The Red Rectangle Nebula, a mere 2,300 light-years away, is a spectacle of sharp angles in a universe of curves. Through a telescope, it does not look like a typical spherical planetary nebula. Instead, it presents a distinct X-shape like two cones set base to base, with what appear to be concentric rungs connecting them, giving it the appearance of a celestial ladder. This startling shape is likely the result of a cosmic dance. At the nebula's heart are two stars, a binary system, locked in a tight orbit. As the older, dying star expels its outer layers, the powerful gravitational influence of its companion star focuses this outflow into two opposing jets. But these jets are not stable. They precess or wobble, much like a spinning top slowing down. Over thousands of years, this wobbling jet has painted the X-shape across space, while periodic puffs of material from the star create the illusion of rungs on a ladder. It is a stunning demonstration of how simple physical processes playing out over eons can create structures of breathtaking complexity and beauty, reminding us that the universe is the greatest artist of all. The universe's potential for life seems limitless, with billions of stars and planets stretching across the cosmos, yet we are met with a profound and unsettling silence. This contradiction is crystallized in a single, deceptively simple question, the heart of the Fermi paradox. Where is everybody? Given the sheer number of worlds and the age of the galaxy, the cosmos should be teeming with civilizations, their signals and artifacts filling the void. Our telescopes, however, hear nothing but the natural background hum of the universe. One way to frame this problem is through the Drake equation, a formula that attempts to estimate the number of active, communicative civilizations in our galaxy. It considers variables like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the fraction of those where life actually emerges. The equation then moves into even more uncertain territory, asking how often life develops intelligence, how often that intelligence builds a technology we could detect, and finally, the length of time such a civilization might broadcast its existence into space. The result of this equation can be anything from just us to millions. The paradox is that all our reasonable estimates point toward a galaxy that should be crowded, yet our observation yields a ghost town. So what is the Great Filter? This is a chilling hypothesis proposing that there is at least one nearly insurmountable barrier, a critical step in the evolution of life that is extraordinarily difficult to overcome. Perhaps the filter is behind us, maybe the jump from simple prokaryotic cells to complex eukaryotic life, a transition that took over 1 billion years on Earth, is exceptionally rare. If that is the case, then we are among the first or the only to have made it through. The more terrifying possibility is that the filter lies ahead of us. It could be that almost every civilization that reaches our level of technological development inevitably discovers the means of its own destruction, whether through nuclear war, engineered pandemics, or a technology we have not yet even conceived. Another solution is far less ominous but equally staggering: the zoo hypothesis. This idea suggests that advanced civilizations are fully aware of our existence but have chosen to place us in a kind of cosmic quarantine. They observe us from a distance, adhering to a strict policy of non-interference until we reach a certain level of maturity, avoiding contact to allow for our natural cultural and technological development. We could be living in a galactic nature preserve, our planet designated as a world not to be disturbed. Or perhaps the simplest answer is the most profound. Maybe the conditions necessary for life, not just any life but intelligent, tool-using, civilization-building life, are so incredibly specific and fragile that they have only occurred once here. In a cosmos of countless stars, we might truly be the only ones asking these questions, the universe's solitary voice echoing in an unimaginably vast and empty cathedral. This cosmic loneliness we feel might be more than just a philosophical dilemma. There is a place in the universe that embodies absolute emptiness, a region so vast and barren it has been called the Great Nothing. This is the Boötes Void, located 700 million light-years from Earth. This spherical region of space stretches an almost incomprehensible 330 million light-years across. To grasp that scale, if our Milky Way galaxy were the size of a grain of sand, the Boötes Void would be a hollow sphere nearly as wide as the entire continent of North America. And within this staggering volume of space, astronomers have found only about 60 galaxies. In a region of the universe that should contain tens of thousands of galaxies, there is almost nothing. This profound emptiness directly challenges one of cosmology's foundational ideas, the cosmological principle. This principle states that on a large enough scale, the universe should look roughly the same in every direction, a homogeneous and isotropic soup of matter and energy. The Boötes Void is not just a minor variation. It is a glaring billion-light-year-wide exception to the rule. How could the process that filled the universe with the cosmic web of galaxies leave behind a desert of this magnitude? One of the most speculative theories suggests this void is not a natural feature of our universe at all, but the scar of a catastrophic collision with another universe in the multiverse. In this scenario, the void is a bubble where the very fabric of space-time was fundamentally altered by the impact, pushing all normal matter out. A less dramatic but equally puzzling explanation is that the Boötes Void is simply a statistical fluke, an extreme outlier in the distribution of cosmic structures. Perhaps it is the universe's largest example of a chance emptiness, a place where, for reasons we do not understand, the initial seeds for galaxy formation simply never took root. The silence from this void is not just a lack of alien signals. It is the silence of space itself, a profound and unsettling emptiness that questions our most basic assumptions about the cosmos. Even our own robotic explorers, sent on grand tours of the solar system, have returned with data that defied understanding for decades. The Pioneer anomaly is a classic mystery born not in the distant cosmos, but right here in our own celestial backyard. The Pioneer 10 and Pioneer 11 spacecraft, after completing their primary missions to Jupiter and Saturn, continued on trajectories that would eventually carry them out of the solar system entirely. As they traveled farther and farther from the Sun, scientists tracking their positions noticed something bizarre. Both spacecraft were experiencing a tiny, constant, and unaccounted-for deceleration, a slight but persistent pullback toward the Sun. This was not part of the predicted flight path. It was as if an invisible hand was gently applying the brakes, a force 10 billion times weaker than gravity on Earth, but measurable and relentless. For years, this minuscule drift was a thorn in the side of physics. It was so small you could dismiss it as a rounding error, yet it was undeniably there, a ghost in the machine of celestial mechanics. The implications, however, were enormous. Could this be a sign of new physics? Perhaps our understanding of gravity itself was incomplete at these vast interplanetary distances. Some speculated that the spacecraft were plowing through a local halo of dark matter, its gravitational drag causing the slowdown. Others proposed exotic ideas involving modifications to Einstein's theory of general relativity. The mystery persisted for over 20 years, a constant nagging puzzle. The solution, when it finally came, was a masterclass in scientific humility. A dedicated team of researchers embarked on a painstaking forensic investigation, digging through decades-old engineering documents and telemetry data. They built a complete and incredibly detailed thermal model of the Pioneer spacecraft. These probes were powered by radioactive thermoelectric generators, which produced heat as a byproduct of generating electricity. The team realized that this heat was not radiating away from the spacecraft uniformly. A little more heat was being emitted from the back of the craft's main antenna dish than from the front. This anisotropic or directionally lopsided radiation of thermal photons was acting like a tiny, continuous photon rocket, providing just ENOUGH Chinese letter to produce the exact deceleration that had baffled scientists for so long. The Pioneer anomaly was not a flaw in the laws of physics, but a subtle engineering effect that had been overlooked. It serves as a powerful reminder that sometimes the most profound mysteries have the most ordinary explanations, hiding in plain sight all along, waiting for us to look closely enough. Our galaxy, the Milky Way, is not the serene island of stars it appears to be. It is a predator. Across the cosmos, a silent, violent feast has been underway for billions of years, a process astronomers call galactic cannibalism. Larger galaxies, like our own, use their immense gravitational pull to tear apart and consume smaller neighboring galaxies. This is not a gentle merger. It is a brutal act of cosmic digestion. You can see its evidence in the halo of our own galaxy, where strange, looping rivers of stars flow in great arcs, completely disconnected from the Milky Way's familiar spiral arms. These are stellar streams, the ghostly remains of dwarf galaxies that ventured too close and were shredded by our galaxy's gravity. One of the most prominent examples is the ongoing destruction of the Canis major dwarf galaxy. Right now, this unfortunate companion is being unraveled, its stars stripped away in a long, looping ribbon that wraps around the Milky Way. We are actively consuming another galaxy, and its dismembered corpse is scattered throughout our celestial neighborhood. This carnage is not just a relic of the past, it points toward an even more colossal event in our future. the Milky Way is on a direct collision course with the Andromeda Galaxy, our largest galactic neighbor. In approximately 4.5 billion years, these two spiral giants will begin a gravitational dance that will utterly transform both. They will not simply crash through one another like solid objects. Instead, their stars are so far apart that direct stellar collisions will be incredibly rare. But gravity will weave the two galaxies into an intricate tapestry, pulling long, brilliant tails of stars out into intergalactic space before they settle into a new, larger galaxy, most likely a featureless elliptical blob. This sounds apocalyptic, and on a galactic scale it is. Yet this destruction is also the primary engine of cosmic creation. The violent gravitational forces during these collisions compress vast clouds of hydrogen gas, triggering ferocious waves of new star formation. The chaos seeds the universe with new solar systems. The largest, most majestic galaxies we see today, including our own Milky Way, were built over eons through this very process of violent assimilation. Galactic cannibalism is the universe's way of building empires from the ruins of its smaller kingdoms. This predatory dance of galaxies seems to orchestrate the cosmos, yet sometimes a solitary messenger arrives from the void between them. In 2017, our solar system received an unexpected visitor from a place far beyond our own. The Pan-STARRS telescope in Hawaii detected a faint point of light moving at such a blistering speed that its trajectory could only mean one thing. It was not from here. This was Oumuamua, the first interstellar object ever observed within our solar system, a scout from the vast galactic ocean. Its very name means scout or messenger from the distant past in Hawaiian, and it lived up to that title by delivering a series of profound puzzles. The first was its shape. As it tumbled through space, the way its brightness fluctuated dramatically suggested an object that was not spherical, nor even a typical lumpy asteroid. The data pointed to something truly extraordinary, an object with an extreme, elongated form, perhaps 10 times as long as it was wide. Imagine a cosmic cigar or a pancake tumbling end over end through the blackness. Nothing we have ever seen in our own solar system looks quite like that. The second and far more baffling mystery was its motion. As Oumuamua swung around the sun and began its journey back out into interstellar space, something strange happened. It sped up. This is a classic behavior for comets. As a comet's icy surface is heated by the sun, it vents gas and dust, creating a visible coma and tail that act like a natural rocket engine, giving it a push. But Oumuamua showed no coma, no tail, no outgassing whatsoever was detected. It was accelerating as if by an invisible force, a non-gravitational acceleration with no apparent cause. This bizarre combination of traits, the strange shape and the unseen engine, ignited a firestorm of scientific debate. How could an object speed up without the telltale signs of a comet? One theory proposed it was a fractal dust aggregate, a fragile, porous structure like a cosmic dust bunny, so light that the pressure of the solar radiation itself could have been enough to push it along. Another, more recent idea suggested it could be a chunk of solid molecular nitrogen, a kind of nitrogen iceberg that had been chipped off the surface of a Pluto-like world in another star system. As this exotic ice sublimated directly from solid to gas in the heat of the sun, it could have provided the necessary thrust without producing the dusty signature of a normal comet. Then there is the more sensational and highly debated hypothesis put forward by Harvard astronomer Avi Loeb. He asked if we should consider the possibility that Oumuamua was not natural at all, but a piece of advanced technology. Perhaps it was a light sail, a vast, thin sheet designed to be pushed by starlight, which would explain its unusual shape and its acceleration without any visible exhaust. While most of the scientific community favors a natural explanation, the very fact that such a possibility can be seriously discussed underscores how truly anomalous this object was. Oumuamua is now long gone, a silent traveler fading back into the depths, It came, it confounded, and it left, leaving behind a single, indelible message. The universe is capable of crafting wonders that we have not even begun to imagine. But even as we contemplate these interstellar travelers, our own solar system holds a boundary that makes no sense. Far beyond the orbit of Neptune, in the deep freeze of the outer dark, lies a ring of icy worlds known as the Kuiper Belt. This is the solar system's final frontier, a vast junkyard of primordial debris left over from the planet's formation. For decades, our models suggested this population of objects should continue, gradually thinning out as you move farther from the Sun, but that is not what we see. Instead, we find a cliff, roughly 50 astronomical units from the Sun, a distance that places it well beyond Pluto. The number of Kuiper Belt objects doesn't just slowly decline. It plummets. It is as if you were walking through a dense forest that abruptly ends at a sheer, unnatural edge with nothing but empty plains beyond. This is the Kuiper Cliff, and its existence is a direct violation of our most fundamental understanding of how planetary systems are born. A protoplanetary disk, the cloud of gas and dust that forms around a young star, should have deposited material in a smooth, continuous gradient. There is no obvious reason for the solar system's construction crew to have just stopped working at this specific distance, so what swept this region clean? The most compelling and tantalizing theory points to the gravitational influence of an unseen world. The hypothetical planet 9, a planet potentially several times the mass of Earth, is thought to be tracing a vast, elliptical orbit far out in the solar system's wilderness. As this giant makes its immensely long journey around the Sun, its gravity would act like a cosmic shepherd, its repeated passes over billions of years stirring up the orbits of the icy objects in that distant belt. Some would be flung inward, others sent careening out into interstellar space, leaving behind the stark, empty border we observe today. This would be the ghost of a planet, its presence inferred only by the void it has carved. Yet, despite years of searching, Planet 9 remains a shadow. Its orbit is so vast that a single trip around the Sun could take 20,000 years, making its current location a matter of intense speculation. Is it hiding in the glare of the galactic core, or is it simply too faint for our current telescopes to pick out? The Kuiper Cliff stands as a silent, gravitational signature, a puzzle etched into the frozen depths of our own cosmic backyard, daring us to find the giant that must be lurking in the dark. This apparent alignment in the very cradle of creation is so unsettling that scientists named it the axis of evil. It refers to a bizarre and deeply controversial pattern found in the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This ancient light is not perfectly uniform. It is a mosaic of tiny temperature fluctuations, hot and cold spots that represent the seeds from which all galaxies eventually grew. According to our most fundamental cosmological principles, these spots should be randomly scattered across the sky, a cosmic fingerprint with no preferred direction. Yet when we map them, a strange correlation emerges. These primordial seeds appear to be subtly aligned with the plane of our own solar system and the direction of our galaxy's spin. It is as if the universe's oldest fossil is pointing a finger directly at us. This should not be. The standard model of cosmology rests upon the Copernican principle, the profound idea that we do not occupy a special or privileged place in the universe. The cosmos should look roughly the same from any vantage point. The axis of evil suggests the opposite. It hints that our location might in fact be special, that we are seeing a fundamental anisotropy in the universe, a preferred direction baked into space-time itself from the very beginning. Could this be a monumental flaw in our understanding of the Big Bang? Perhaps it is not a cosmic signal at all, but a local contaminant, some unknown emission from dust within our own Milky Way that is muddying the pristine signal. Or, in the most radical interpretation, is it evidence that our universe is not what it seems, that it is somehow lopsided or textured in a way we have never dared to imagine? The axis of evil remains a profound thorn in the side of cosmology, a whisper from the dawn of time that we are not yet able to understand. These unimaginably powerful magnetic fields are born from the ultimate collapse of a star's core. When a massive star, many times larger than our Sun, exhausts its nuclear fuel, it no longer has the outward pressure to support its own immense weight. The core collapses catastrophically in a supernova explosion. What remains is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. A magnetar is a neutron star pushed to an even more extreme limit. During its violent birth, if the collapsing core is spinning rapidly enough, the convective currents of superheated, electrically charged material can act like a colossal dynamo, amplifying the star's already intense magnetic field to truly monstrous levels. This is the genesis of a magnetar, a cosmic powerhouse whose influence extends far beyond its tiny physical form. The sheer force of its magnetism can literally twist the atomic structure of matter. The electron clouds that surround an atom's nucleus are warped into long, thin cylinders. Chemistry as we know it becomes impossible in such an environment, as atoms cannot form bonds or molecules. A magnetar's wrath is not confined to its immediate vicinity. A star quake on its surface, a sudden cracking of the ultra-dense crust, can release a flash of gamma rays so energetic that if one occurred within 10,000 light-years of Earth, it could strip away our planet's protective ozone layer, triggering a mass extinction event. We have detected such events, known as soft gamma repeaters, from distant magnetars. These are not single explosions, but repeated, violent outbursts of high-energy radiation, the star shuddering and cracking under the immense strain of its own magnetic field. This violent physics might also hold the key to one of our earlier mysteries. The incredible energy released in a magnetar flare, channeled and focused by that impossibly strong magnetic field, could be the engine behind some fast radio burst. In a fraction of a millisecond, a star quake could launch a blast of radio waves so powerful it briefly outshines entire galaxies, a final, desperate signal from a star that has become a prisoner of its own unimaginable power. Even the most absolute darkness in the universe may not be a final resting place. Stephen Hawking made a stunning theoretical discovery about black holes, revealing they are not entirely black. They are predicted to glow, emitting a faint whisper of radiation that slowly, over eons, causes them to evaporate completely. This Hawking radiation arises from the strange, probabilistic nature of empty space itself, where virtual particle pairs constantly flicker in and out of existence. Normally, these pairs annihilate each other instantly, but at the very edge of a black hole, the event horizon, one particle can fall in while its partner escapes, stealing a tiny amount of the black hole's mass and carrying it away into the cosmos. This means a black hole has a finite life, destined to eventually vanish in a final, faint puff of energy. Yet this beautiful solution created one of the most vexing problems in all of physics, the black hole information paradox. In our universe, information is sacred. The quantum state of every particle that falls into a black hole, every atom of a star, every bit of data that defined what it was, is supposed to be fundamentally preserved. You might not be able to retrieve it, but according to quantum mechanics, it cannot be erased. Hawking's calculations suggested that the radiation escaping a black hole is completely random, a featureless thermal hum. It carries no information about the specific things that were consumed. When the black hole finally evaporates, all that intricate information about what fell in seems to vanish forever, violating a core tenet of quantum theory. This is a direct conflict between the two pillars of modern physics: general relativity, which governs gravity and the large-scale structure of spacetime, seems perfectly content to let information be lost down a black hole. Quantum mechanics, which rules the subatomic world, insists this is absolutely impossible. Both theories cannot be correct, so where does the information go? One of the most mind-bending proposals is the holographic principle. It suggests that all the information about everything within the three-dimensional volume of a black hole is not lost inside, but is instead encoded on its two-dimensional surface, the event horizon. Like a cosmic hologram, the data is painted onto the boundary, preserved in the intricate way that the horizon vibrates and shifts as objects fall through it. In this view, the Hawking radiation is not random after all. It is subtly imprinted with this surface information, slowly decoding the black hole's history as it evaporates. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not the smooth gateway predicted by general relativity, but a searing wall of unimaginable energy. The moment you cross it, you would be instantly incinerated. This firewall would resolve the paradox by preventing any information from actually entering the black hole in the first place, but it does so by shattering our classical understanding of what happens at the horizon. The true answer to this paradox remains elusive, a battle of ideas at the very frontier of knowledge. Whatever the solution turns out to be, it will force us to rewrite our understanding of reality, revealing how space, time, and information are woven together in ways we are only beginning to grasp. Even our most fundamental cosmic constants are now being questioned. The Hubble constant, a number representing the universe's current rate of expansion, is supposed to be a fixed value, a single speedometer reading for the cosmos. Yet, two different methods for measuring it are delivering two different, stubbornly incompatible answers. This is the Hubble tension, and it is not a small discrepancy. It is a growing crack in the foundation of modern cosmology. The first method looks back to the very beginning, to the afterglow of the Big Bang itself. The Planck satellite mapped the cosmic microwave background in exquisite detail, and by analyzing the patterns in that ancient light, scientists can calculate what the expansion rate should be today, assuming our standard model of the universe is correct. This method gives us a very precise value. The second method measures the universe as it is now in our local cosmic neighborhood. Astronomers use a cosmic distance ladder, starting with reliable mile markers like Cepheid variable stars, whose predictable pulsations reveal their true brightness, to calibrate the distances to faraway galaxies that host Type Ia supernova. These supernovae are another type of standard candle, exploding with a known intrinsic brightness, allowing us to measure how fast those galaxies are rushing away from us. This local measurement consistently returns a value for the expansion rate that is significantly faster by about 5 to 10% than the prediction from the early universe. Imagine setting two incredibly precise atomic clocks at the same time. You leave one on Earth and send the other on a journey at near light speed. When the traveling clock returns, they should still agree. But in our cosmic experiment, the clocks are telling different times. The early universe clock and the modern universe clock are out of sync, and we cannot explain why. This is not a simple measurement error. The teams using each method have checked and rechecked their work, ruling out known sources of uncertainty. The tension persists, and it is significant. The implications are staggering. It could mean our standard model of cosmology, known as lambda CDM, which beautifully describes a universe dominated by dark energy and dark matter, is incomplete. Perhaps dark energy is not a constant, but an evolving force that has grown stronger over time, giving the expansion an extra push that the early universe data did not predict. Or maybe there is an entirely new type of particle or field, a ghost in the cosmic machine, that our models have not yet accounted for. The Hubble tension is a quiet alarm bell, telling us that something fundamental is missing from our picture of the cosmos, a mystery hiding in plain sight within the very expansion of space itself. Deep within the heart of our own galaxy, a strange and persistent glow defies a simple explanation. This is the galactic center excess, a mysterious fog of high-energy gamma-ray radiation that permeates the core of the Milky Way. For years, the Fermi Gamma Ray Space Telescope has mapped this energetic light, revealing a surplus that shouldn't be there. We know of several natural sources for such radiation, like the spinning corpses of dead stars known as pulsars. But when astronomers add up the light from all the known pulsars and other cosmic objects in that region, there is still a massive amount of gamma rays left over. A brilliant, unexplained excess hangs over the galactic center like an unanswered question. So what is creating this persistent, energetic fog? Scientists are locked in a debate between two compelling possibilities, each with profound implications. The first, more conventional, theory points to a vast, hidden population of millisecond pulsars. These are ancient neutron stars that have been spun up to incredible speeds, rotating hundreds of times per second by siphoning material from a companion star. They would be too faint and crowded together for our telescopes to distinguish as individual points of light, but their collective glow could perfectly explain the diffuse gamma ray signal we see. It would mean we are looking at a stellar graveyard more densely packed with these cosmic lighthouses than we ever imagined. The second possibility is far more exotic and thrilling. This excess could be the first indirect evidence of dark matter. The center of our galaxy is thought to be the most dense concentration of this mysterious substance. According to some leading theories, when two dark matter particles collide, they could annihilate each other in a flash of energy, producing the very gamma rays that Fermi detects. If this is true, then that faint glow is not a veil of stars, but the ghostly afterimage of the universe's most elusive substance finally revealing itself through its own self-destruction. We are essentially watching the shadow of dark matter flicker into view. This makes the galactic center excess one of the most important puzzles in modern astrophysics. Is it a previously unseen class of stellar objects, or is it the signature of a particle that makes up most of the matter in the cosmos? The answer lies in the precise pattern of the light. A smooth, uniform glow would favor dark matter annihilation, while a more clumpy, granular signal would point toward a vast collection of pulsars. For now, the data remains tantalizingly ambiguous, a siren song from the galactic core that promises a revolution in our understanding, if only we can learn to interpret its message. This same geometric perfection appears not only in the deep cosmos but much closer to home, adorning the very face of a neighboring world. At the North Pole of Saturn, a colossal hexagon spins in near-perfect symmetry. This is not a temporary cloud formation but a permanent, towering jet stream, a six-sided wave of wind that has raged for at least 4 decades since the Voyager probes first glimpsed it. The scale is almost impossible to comprehend. Each side of the hexagon is wider than our entire planet, and the whole structure is so vast that 4 Earths could fit comfortably within its boundaries. It is a storm of pure geometry, a cosmic snowflake etched into the atmosphere of a gas giant. How can such an angular, stable pattern persist in the chaotic, fluid dynamics of a planetary atmosphere? Scientists have turned to the laboratory to find answers. By spinning a cylinder of fluid, they can simulate the conditions at a planet's pole. When the rotation speed is just right, instabilities in the fluid can indeed generate standing waves that form into polygons, with a 6-sided hexagon being a particularly stable configuration. This suggests the Saturn hexagon is a kind of planetary scale standing wave, a stable pattern emerging from the interaction between the planet's rapid rotation and the jet streams in its atmosphere. Yet the laboratory models, while compelling, are a vast simplification of the turbulent reality on Saturn. What precise combination of wind speeds, atmospheric density, and planetary rotation locks this pattern in place with such razor-sharp precision, and why has it not degraded or shifted over all these years? The hexagon is a masterpiece of natural physics, a reminder that the laws governing fluids can paint with a surprisingly geometric brush on a planetary canvas. The same cosmic fossil that revealed the axis of evil holds another, equally profound anomaly. A single patch of the sky located in the constellation Eridanus is significantly and mysteriously colder than its surroundings. This is the CMB cold spot, a region of the universe's oldest light that is a staggering 70 microkelvin cooler than the average temperature of the cosmic microwave background. At first glance, this might not sound like much, but on the scale of the entire observable universe, such a large and coherent cold spot is a statistical outlier of immense proportions. It is so extreme that the odds of it occurring by pure random chance are less than 1 in 200, a cosmic roll of the dice that defies easy explanation. This is not a simple imperfection in the data. It is a fundamental challenge to our understanding of the universe's infancy. The standard model of cosmic inflation, the theory that the universe underwent a period of explosive expansion immediately after the Big Bang, predicts a certain kind of randomness in the CMB's temperature fluctuations. The cold spot is too big and too cold to fit neatly within that prediction. So what could have left such a frigid fingerprint on the dawn of time? One leading theory points to a vast cosmic emptiness, a supervoid. This would not be a simple gap, but a spherical region of space hundreds of millions of light-years across that is almost completely devoid of galaxies and galaxy clusters. According to general relativity, as a photon travels through such an immense void, it must climb out of a gravitational well. Since the universe is expanding and the void itself is growing, the well becomes shallower as the photon climbs, causing the photon to lose a tiny amount of energy in a process called the integrated Sachs-Wolfe effect. Over the vast distance of the supervoid, this energy loss would add up, making the CMB light from that direction appear slightly colder, just as we observe. The only problem is finding a void large enough to cause the effect. While astronomers have identified a potential candidate, the Eridanus supervoid, its size may still be insufficient to account for the profound cold we detect, leaving the mystery only partially solved. A far more radical hypothesis suggests the cold spot is not a void at all, but a cosmic bruise. It could be the scar of a collision with another universe during the inflationary epoch. In the multiverse theory, our universe is just one bubble in a frothing sea of space-time foam. If our bubble had bumped into a neighboring one in the first moments of existence, the interaction could have drained energy from that region of space, leaving behind a permanent cold spot in the CMB, a relic of a time before time as we know it began. Whether it is a staggering emptiness or evidence of a primordial collision, the cold spot remains a profound reminder that the universe's first light still holds secrets we are only beginning to read. Even the most massive objects in the cosmos are not immune to being thrown out. Picture a supermassive black hole, the gravitational anchor of an entire galaxy, suddenly hurled into the void at millions of miles per hour. These are runaway black holes, and their existence reveals a universe of unimaginable violence. The mechanism for this cosmic eviction is as elegant as it is powerful. When two supermassive black holes in a galactic core finally spiral into each other and merge, they do not come together quietly. They churn the fabric of space-time itself, sending out ripples known as gravitational waves. If the merger is asymmetrical, if the two black holes are of unequal mass or have misaligned spins, the final blast of gravitational waves can be emitted more strongly in one direction. Just as a gun recoils when fired, the newborn, more massive black hole experiences a tremendous kick in the opposite direction. This recoil can be so powerful it exceeds the galaxy's escape velocity, booting the black hole from its home entirely. We are now finding evidence of these celestial fugitives. Astronomers have spotted incredibly bright, point-like sources of light, quasars powered by supermassive black holes that are completely separated from any visible galaxy. They blaze alone in the darkness, their host galaxies presumably left behind, stripped of their central gravitational heart. The implications are staggering. A galaxy that loses its central black hole may find its future evolution dramatically altered, potentially unable to regulate star formation or grow its central bulge. Furthermore, these rogue black holes wandering the intergalactic voids become invisible predators. Any star system unfortunate enough to wander near one would be torn apart, its material flaring briefly as a final beacon before being swallowed by the darkness. This process scatters the most destructive objects in the universe far and wide, seeding the cosmos with lonely monsters on an endless, silent journey. Our most fundamental origin story holds a tiny, persistent flaw. The universe's first 3 minutes were a frenzied nuclear forge, a period known as Big Bang nucleosynthesis. During this brief, searing hot epoch, the primordial soup of particles cooled just enough to fuse into the very first light elements. The calculations for this process are a triumph of modern cosmology. The predicted amounts of deuterium, helium, and hydrogen match what we observe throughout the cosmos with stunning precision. Yet for one single element, the theory fails completely. The models tell us there should be about 3 times more lithium-7 in the oldest stars than we can actually find. This is the cosmological lithium problem, a small number with enormous implications. How could our understanding of the universe's first moments be so perfectly right for some elements and so clearly wrong for another? One possibility takes us into the realm of new physics. Perhaps an unknown type of particle was present in that early cosmic soup, a relic from an even earlier time. Certain theoretical particles, like supersymmetric ones, could have interacted with the nascent nuclei, effectively destroying lithium as it formed or altering the nuclear reaction pathways just enough to leave the deficit we see today. This would mean the lithium problem is not a flaw, but a clue, a tiny fingerprint left by a fundamental particle that has so far eluded all our detectors. The other possibility turns the problem on its head. Maybe our models of the Big Bang itself are correct, and the error lies in our reading of the ancient stellar fossils we use to test them. We measure primordial lithium by looking at the atmosphere of the most ancient stars in the halo of our galaxy, stars that formed from nearly pure primordial gas. But what if these ancient stars are not the pristine time capsules we believe them to be? Their interiors are colossal nuclear reactors, and internal processes we do not fully understand could have slowly dragged lithium from their surfaces down into their cores, where it was destroyed over billions of years. Alternatively, the gentle settling of heavier elements under the force of gravity could have made their surfaces appear more lithium-poor than they truly are. This would mean the problem is not with the cosmos, but with our understanding of stellar archaeology. We are left with a beautiful puzzle. Is the lithium discrepancy a sign of exotic new physics waiting to be discovered, or is it a humbling reminder that even the oldest stars in the sky still hold secrets about their own inner lives? The answer is written in that missing lithium, a cosmic oversight from the dawn of time. Sometimes the most profound mysteries are hidden in what we do not see. Deep within the colossal particle colliders that smash matter together at nearly the speed of light, physicists occasionally record an event where energy seems to simply vanish. It disappears from the detectors as if it has slipped into another dimension. One of the most speculative yet captivating explanations for this missing energy is the concept of unparticles. This is not a new particle in the traditional sense. Our entire reality is built from a family of discrete particles, each with specific properties and masses like quarks and electrons. Unparticles, by contrast, are theorized to be something else entirely, a continuous and scale-invariant substance. Scale invariance means it looks the same at all levels of magnification, possessing no single defining mass or size. Think of it not as a collection of individual marbles, but more like a strange, fundamental fog that permeates everything. When ordinary particles collide in an accelerator, they could potentially interact with this unparticle sector, transferring energy into it. Because this unparticle stuff does not behave like a recognizable particle, it would not leave a track in our detectors. The energy just seems to be gone, creating an inexplicable imbalance in the accounting of the collision event. If proven to be real, unparticles would represent a state of matter so alien that it forces us to rewrite the standard model of particle physics, the rulebook for the entire universe. It would mean that reality is built upon a foundation far stranger and more fluid than we ever conceived, a hidden ocean of continuous substance whose ripples we are only now learning to sense. The graceful spiral arms of a galaxy like our own are not solid structures but temporary patterns, like vast cosmic traffic jams moving through a sea of stars. This is the essence of density wave theory, which suggests that spiral arms are regions of compressed gas and dust where star formation ignites, creating the luminous trails we see. These waves rotate around the galactic center at their own stately pace, independent of the frantic orbital speeds of the individual stars, which pass in and out of the arms like cars flowing through a slow-moving construction zone. Over a galactic year, the time it takes for a star like our Sun to complete one full orbit, this elegant model should hold true. Yet when astronomers run the numbers, a curious discrepancy emerges. Given the rotation speeds of stars and the predicted lifespan of these density waves, the majestic spiral patterns in many galaxies should have wound up tightly, collapsing into a featureless disk long ago. They are either too short-lived or, in other cases, persist for far longer than the theory readily allows. Our own Milky Way presents this puzzle perfectly. Its spiral arms are prominent and well-defined, but based on the differential rotation of its stars, the pattern should have dissolved after just a few orbits, a mere fraction of the galaxy's actual age. So what force is constantly refreshing this celestial artwork, preventing it from fading into chaos? The answer appears to lie not in a single wave, but in a symphony of repeated gravitational nudges. The relentless tug of satellite galaxies, like the large and small Magellanic Clouds as they swing past on their long orbits, can repeatedly pluck the galactic disk, stirring up new waves and reinforcing the existing spiral structure. Even more influential is the galaxy's own central bar, a dense elongation of stars at the heart of many spirals. As this bar rotates, its immense gravitational field acts like a colossal paddle in a pond, continually sloshing the surrounding stars and gas and tirelessly sustaining the spiral pattern we see today. The spiral arms we admire are not permanent fixtures, but dynamic, living structures, their beauty maintained by an ongoing gravitational ballet that plays out over billions of years. Even the most basic inventory of the cosmos contains a colossal accounting error. Our most precise calculations, based on the afterglow of the Big Bang, tell us exactly how much normal matter should exist, the protons and neutrons that form every star, planet, and person. Yet when we tally up all the visible galaxies, gas clouds, and dust, we find that a staggering 30 to 40% of this ordinary stuff is simply missing. This is the missing baryon problem, a cosmic case of misplaced matter. These are not the elusive particles of dark matter. This is the very substance of our reality, and almost half of it has vanished without a trace. So where could it possibly be hiding? The leading suspect is a ghostly, searing hot web known as the Warm-Hot Intergalactic Medium, or WIM. Picture the cosmic web of dark matter, that invisible scaffolding upon which galaxies are built. Stretching along those vast, invisible filaments, in the immense voids between galactic clusters, exists a diffuse fog of superheated gas. This is not a cold, empty darkness, but a space filled with matter so incredibly hot at millions of degrees that it does not emit visible light. Instead, it glows faintly in high-energy X-rays, a radiation that is notoriously difficult to detect across cosmic distances. Finding this WIM is like trying to see the subtle heat haze rising from a desert highway from 1,000 miles away. Its signature is incredibly faint, and it is spread so thinly across billions of light-years that it has eluded our telescopes for decades. We have, however, caught glimpses. When the light from a brilliant, distant quasar travels through these filaments on its way to Earth, the superheated gas in the WIM absorbs specific wavelengths of that light. By analyzing the quasar's spectrum, astronomers can see the ghostly fingerprints of highly ionized oxygen and other elements, revealing the presence of this vast hidden reservoir. These observations suggest that this warm, hot intergalactic medium could indeed hold the key to the missing baryon problem, containing all the lost ordinary matter in the form of a thin cosmic plasma woven between the stars. It appears the universe has not lost its matter at all. It has simply hidden it in plain sight, in the most expansive and difficult-to-detect places imaginable. The universe has a strict speed limit for cosmic particles, a theoretical boundary known as the Greisen-Zatzeping, Kuzmin cutoff. This rule states that protons traveling across the cosmos with impossibly high energy should be slowed down by the faint leftover radiation from the Big Bang. They would collide with these ancient photons, losing their energy bit by bit until they fall below the cutoff threshold. This means any particle we detect with energy beyond this limit should have come from a source relatively close to our own galactic neighborhood, a short cosmic commute away. Yet we do detect them. These are ultra-high-energy cosmic rays, single subatomic particles carrying the kinetic energy of a professionally thrown baseball, all packed into a speck smaller than an atom. They are the most energetic particles ever measured, and their existence is a profound violation of our expectations. The greater mystery is not just that they arrive, but that we cannot find where they came from. Their paths are scrambled by interstellar magnetic fields during their journey, making it nearly impossible to trace them backward to a specific point in the sky. When we look in the general directions from which they come, we find no obvious cosmic power plants, no nearby active galactic nuclei, no brilliant gamma-ray bursts, no colliding galaxies powerful enough to have launched them. It is as if a cannonball has been fired into a crowded square, but when you turn to look, there is no cannon. The accelerators for these particles must be monstrous engines of destruction, operating on a scale we can barely comprehend, and they are hiding in plain sight within the local universe, their identities shielded by the very emptiness they punctuate with such violent, fleeting messengers. These stellar giants are so unstable they can tear themselves apart while still shining. Luminous blue variables are the rarest and most massive stars we know of, cosmic behemoths living on a razor's edge. They are hundreds of times more massive than our Sun and glow with a ferocious, hyper-luminous blue light, radiating the energy of millions of stars like our own. But this brilliance comes at a terrible cost. These stars are fundamentally unstable, wrestling with their own immense gravity. Their outer layers are so loosely bound that the star can no longer hold itself together, leading to violent, unpredictable eruptions. In a single event, a luminous blue variable can eject multiple times the entire mass of our Sun into space, creating a colossal shell of ejected gas and dust around it. This causes the star's brightness to fluctuate wildly, sometimes dimming for years before blazing back to its full fury. The most famous example is Eta Carinii, a star system that underwent a great eruption in the 1840s. For over a decade, it became the second brightest star in the night sky, ejecting at least 10 solar masses of material and forming the beautiful, expanding homunculus nebula we see today. This was not a supernova, but a stellar tantrum of epic proportions. The ultimate fate of these volatile monsters is one of astrophysics' great debates. Do they finally exhaust their fuel and collapse directly into a black hole, vanishing from the visible universe without the traditional fireworks of a supernova? Or at the very upper limit of their mass, do they become the progenitors for the most titanic explosions possible, a pair instability supernova? In this cataclysmic end, the core of the star becomes so hot that light itself spontaneously transforms into matter and antimatter pairs. This process robs the core of the radiation pressure holding it up, causing a runaway collapse and a thermonuclear explosion so violent that it completely obliterates the star, leaving no remnant behind. It is a total self-annihilation that can outshine an entire galaxy. So every luminous blue variable we observe is a star living on borrowed time, a cosmic question mark whose final, violent act could rewrite our understanding of stellar death. This bizarre connection between the smallest particles suggests a cosmos woven together by invisible threads. At the heart of quantum mechanics lies a phenomenon so strange that even Einstein famously dismissed it as spooky action at a distance, known as quantum entanglement. It begins when two particles, like photons or electrons, are created together or interact in a specific way. From that moment on, their properties become inextricably linked, no matter how far apart they travel. If you measure the spin or polarization of one particle and find it is pointing up, its entangled partner, even if it is now on the other side of the galaxy, will instantly be found pointing down. The information between them seems to travel faster than light, a notion that defies our classical understanding of reality. For decades, this was a philosophical debate. Then came the experiments, using everything from fiber optic cables stretching between cities to satellites beaming photons down to telescopes on the ground. Physicists have repeatedly confirmed that entanglement is real. They have sent entangled particles over distances of hundreds of kilometers, and the correlation between them holds every single time. The universe at its most fundamental level is not just made of separate, isolated bits. It is a deeply interconnected web. This undeniable fact forces a staggering question upon us. If two particles can be entangled across a continent, what is the ultimate limit of their reach? Could this spooky action operate on a galactic or even a universal scale? The implications are mind-bending. It suggests a cosmos where every part, from the dust on an asteroid to the heart of a distant quasar, might share a ghostly, instantaneous connection. Perhaps the universe did not just create separate objects during the Big Bang, but one single, entangled system that has been stretching and evolving ever since. This idea of universal entanglement could offer a new way to understand the cosmos's underlying unity, but testing such a concept presents almost insurmountable challenges. The delicate quantum states are easily destroyed by any interaction with their environment, a process called decoherence. Maintaining entanglement across the vast, noisy emptiness between stars seems practically impossible with our current understanding. Yet the theoretical possibility remains, a whisper that the universe might be far more intimately connected than the lonely void of space would have us believe. This silence from the cosmos might be the most important message it could ever send. The Great Filter hypothesis gives this eerie quiet a terrifying shape, proposing a single, critical wall that almost no life can climb. Think of evolution as a grand, cosmic obstacle course with one hurdle so high it effectively eliminates every runner. The question that should haunt us is not just if this filter exists, but where it lies in our own timeline. One possibility offers a strange comfort. Perhaps the filter is behind us. The leap from non-living chemistry to the first self-replicating cell might be a miracle of such astronomical improbability that it has only happened once. Or maybe the true bottleneck was the transition to complex multicellular life, a jump that took over 1 billion years on Earth. If this is the case, then we are the inconceivable winners, the first and only species in our galactic neighborhood to have made it this far. The universe is empty because we are the pioneers. The alternative is far more chilling. What if the filter is not in our distant past, but in our immediate future? It could be that the development of advanced technology contains the seeds of its own destruction. The moment a species gains the power to manipulate the fundamental forces of nature, it also gains the power to erase itself. This could be through nuclear annihilation, a fate we have already glimpsed. It could be through a genetically engineered pandemic, a product of our own ingenuity turning against us. Or it could be a technology we have not yet even conceived, an invention like self-replicating nanobots that consume the biosphere, or an artificial intelligence whose goals do not align with our survival. In this scenario, the silence of the galaxy is a graveyard. It is the sound of countless civilizations that reached our present level of development, only to inevitably trigger their own extinction. The great filter, therefore, becomes a mirror. When we look up at the quiet stars, we are not just wondering about aliens, we are asking the most urgent question about our own destiny. Are we poised to become our own filter, just one more flash in the dark that briefly flickers and then vanishes forever? Black holes are cosmic one-way streets, but what if the universe also has exits? Theoretically, white holes are their perfect opposites, regions where matter and energy can only pour out, and nothing, not even light, can ever cross inwards. They emerge as mathematically valid solutions to Einstein's field equations of general relativity, a perfectly symmetrical counterpart to the dark, all-consuming nature of a black hole. Yet while the math permits them, physics as we understand it stands firmly in their way. A white hole would fundamentally violate the second law of thermodynamics, the universal principle that disorder, or entropy, always increases. Such an object, constantly spewing out ordered energy without ever absorbing anything, would be like a perpetual motion machine, creating order from nothing and causing the total entropy of the universe to decrease. This is why most scientists conclude that while white holes are a beautiful idea, they are likely impossible in our reality. Still, the concept is too tantalizing to abandon completely. One of the most profound speculations is that the Big Bang itself was a primordial white hole, a single, ultimate eruption of all space, time, and matter from a singularity. Another captivating idea, a staple of science fiction, posits that a white hole could be the distant other end of a black hole's wormhole. In this view, anything that falls into a black hole might not be crushed into oblivion, but instead could be hurled across the cosmos, emerging from a white hole in another time or another universe entirely. This would transform black holes from tombs into gateways, and white holes into cosmic fountains of rebirth. For now, they remain one of the most fascinating what-ifs, a ghost in the machine of Einstein's universe, reminding us that the laws of physics can sometimes point to wonders that reality itself forbids. Even the most resilient stars face a final, absolute boundary. Deep within the heart of a neutron star, a cosmic tug-of-war rages between two titanic forces. On one side, the intense pressure generated by the quantum degeneracy of neutrons fights to hold the star up. On the other, the star's own immense gravity works tirelessly to crush it into a point of infinite density. The line that separates this stalemate from total collapse is the Tolman-Oppenheimer-Volkoff limit. This is the maximum possible mass a neutron star can possess before it inevitably gives in, vanishing from the visible universe to become a black hole. It is the ultimate weight limit for a sphere of degenerate matter, the final verdict on stellar survival. Yet, for such a critical cosmic rule, we do not know its precise number. The exact value of this limit, thought to be somewhere between 2 and 3 times the mass of our Sun, is not a fixed constant. It depends entirely on the equation of state of neutron star matter, a property we cannot replicate or observe directly. Inside a neutron star, matter is compressed to densities so extreme that atomic nuclei dissolve into a seething ocean of neutrons, with other exotic particles like hyperons and free quarks potentially swimming in the mix. Is this bizarre substance relatively soft, easily compressible, or is it incredibly stiff, resisting further collapse with ferocious strength? A soft equation of state would mean a lower mass limit, a star that buckles under less weight. A stiff equation of state would allow for heavier, more massive neutron stars to exist before they finally fail. For decades, this was a question for theoretical physics alone, confined to supercomputer models. That changed dramatically with the first detection of gravitational waves from a neutron star merger, an event known as GW 178017. When those two dead stars spiraled into each other, the ripples in spacetime they produced carried vital information about their nature. By analyzing the gravitational wave signal, scientists could infer the masses and the tidal deformability of the neutron stars, a direct measure of how stiff their internal material truly is. This single cosmic collision provided a crucial data point, ruling out some of the stiffest equations of state and suggesting the Tolman-Oppenheimer-Volkoff limit might lie closer to 2.5 solar masses. Every new neutron star merger we detect is another piece of the puzzle, another step toward pinning down this fundamental number that dictates the final fate of the universe's most massive stellar corpses. Our galaxy breathes. It exhales colossal plumes of hot gas and inhales cool, dense clouds in a slow, majestic rhythm that spans thousands of light years. This is the galactic fountain model, the dynamic cycle that sustains star formation across the eons. At the heart of this process are the most violent events in a galaxy's life: supernova explosions and the powerful stellar winds from massive young stars. These titanic forces act like cosmic bellows, blasting scorching gas out of the relatively thin galactic disk and hurling it high up into the halo, a vast spherical region of sparse matter that surrounds the galaxy. This ejected plasma, heated to millions of degrees, rises until it reaches a point where it begins to cool, condensing into massive, dark clouds of neutral hydrogen. Then, under the relentless pull of the galaxy's gravity, these clouds begin their long fall back toward the luminous disk below, raining down like a cosmic waterfall to replenish the raw material for new stars. This elegant model beautifully explains the presence of high-velocity clouds we observe around our own Milky Way, great arcs of gas that seem to be either rising from or falling onto the starry plane. It reveals a galaxy that is not a closed system but a self-regulating engine, recycling its own material to fuel its future. Yet this grand cycle holds its own profound puzzles. How exactly do these immense, diffuse clouds of hot gas high in the halo manage to cool and clump together so effectively? The physics of this condensation is incredibly complex, involving turbulent mixing, magnetic fields, and radiative cooling that we are only beginning to understand. Even more fundamental is the question of balance. Is this fountain a perfect closed loop, or is the galaxy slowly losing material to intergalactic space with every exhale, or perhaps gaining it with every inhale from the cosmic web? The precise accounting of this galactic scale recycling, the inflow versus the outflow, remains one of the most active and critical areas of research in understanding how galaxies live and die. This celestial fountain is the very breath of the galaxy, and we are only now learning to listen to its rhythm. There is a precise and beautiful rule that governs the death of stars like our own sun, a cosmic boundary known as the Chandrasekhar limit. It states that a white dwarf, the exposed, ultra-dense core left behind after a star sheds its outer layers, cannot exceed a mass of approximately 1.4 times that of our Sun. This number is the ultimate threshold. Within a white dwarf, the incredible pressure of gravity trying to crush the star is held at bay only by a quantum mechanical force called electron degeneracy pressure. The electrons, packed together as tightly as the laws of physics will allow, simply refuse to be squeezed any further. But if the white dwarf accretes more mass, perhaps by siphoning gas from a companion star, it pushes past this 1.4 solar mass limit. At that critical moment, the electron pressure instantly fails. The star can no longer support its own weight, and it collapses in on itself in a heartbeat. This triggers a runaway thermonuclear explosion that rips the entire white dwarf apart in a cataclysm so uniform and so brilliant we call it a Type Ia supernova. This uniformity is its greatest gift to astronomy, because these supernovae always explode at almost exactly the same true brightness. They act as perfect standard candles. When astronomers see one in a distant galaxy, they know its intrinsic luminosity. By measuring how dim it appears from Earth, they can calculate the distance to its host galaxy with incredible precision. It was precisely this property that allowed scientists in the late 1990s to make the landmark discovery of dark energy. By using Type Ia supernova as cosmic mile markers, they found that the most distant ones were fainter than expected, proving the universe's expansion is accelerating. The Chandrasekhar limit is more than a stellar rule. It is the key that unlocked the greatest mystery of modern cosmology. Yet the universe loves to test its own laws. Astronomers have now found a handful of potential super Chandrasekhar mass white dwarfs, stellar remnants that seem to be more massive than the limit should allow. How can they exist? One possibility involves incredibly fast rotation, where the star's spin provides extra support against collapse. Another theory suggests these white dwarfs may possess bizarre, ultra-strong magnetic fields that help prop them up. Studying these exceptional objects pushes our understanding of matter under the most extreme conditions imaginable, forcing us to ask if the Chandrasekhar limit is a firm wall or a gate that can be opened under the right circumstances. Even our best theories of reality can produce a number so wrong it threatens to unravel everything we think we know. This is the vacuum catastrophe, arguably the most severe mismatch between prediction and observation in all of science. The problem lies in the energy of empty space itself, the quantum vacuum. According to quantum field theory, the vacuum is not truly empty. It is a seething, foaming sea of virtual particles that constantly pop in and out of existence. Every cubic centimeter of space, even the deepest, darkest void between galaxies, should be fizzing with this underlying energy. When physicists calculate the total energy density this quantum frenzy should contribute, they arrive at a figure. Then we can measure the actual energy density of space by observing the effects of dark energy on the universe's expansion. The two numbers should be the same. They are not even close. The theoretical prediction is a number so astronomically large it is almost meaningless, a 1 followed by 120 zeros. The value we actually observe from dark energy is almost zero. To grasp the scale of this error, the theoretical value is 10 to the power of 120 times larger than the observed value. This is not like being off by a factor of 2 or 10. This is a miscalculation so vast it exceeds the number of atoms in the entire observable universe. It means our most fundamental theory of the small-scale world and our most precise measurements of the large-scale cosmos are in direct, violent contradiction. How can our understanding be so spectacularly wrong? One potential resolution is as philosophical as it is physical, the anthropic principle. This idea suggests that the value of the vacuum energy is not fixed by a fundamental law, but can vary across different regions of a vast multiverse. In almost all of these regions, the vacuum energy is enormous, and the universe either collapses instantly or expands so fast that no stars, planets, or life can ever form. We, of course, find ourselves in one of the incredibly rare bubbles where the value is mysteriously small, allowing galaxies to coalesce and life to evolve. In this view, there is no deeper explanation. We observe this specific value because it is the only one that permits our existence. It is a cosmic coincidence that selects for observers. Other physicists find this answer deeply unsatisfying, believing it halts scientific inquiry. They argue the catastrophe points to a fundamental flaw in our understanding of the quantum vacuum. Perhaps the frenetic activity of virtual particles somehow cancels itself out to near perfection, leaving only the tiny residue we see as dark energy. Or maybe gravity, described by general relativity, does not couple to the quantum vacuum energy in the way we currently assume. The vacuum catastrophe is a silent, profound crisis at the heart of physics, a screaming error in our math that tells us a crucial piece of the cosmic puzzle is still missing from our grasp. This bizarre state of matter could rewrite the very definition of a star. Inside a neutron star, matter is crushed into a sea of neutrons, but the pressure might not stop there. Some theories propose that under such immense strain, the neutrons themselves break down into their fundamental components, up quarks, down quarks, and strange quarks, creating a new, stable substance known as strange matter. A star made from this exotic brew would be a strange star, a single, city-sized atomic nucleus containing a near-infinite number of quarks all bound together. This strange matter could be the true ground state of matter in the universe, more stable than even the iron in the core of a normal star. If this is true, a strange star would be effectively indestructible. A tiny fragment of this material, a strangelet, could theoretically convert any ordinary matter it touched into more strange matter, a chain reaction that would transform a planet into a lump of exotic quarks in an instant. Fortunately, no such event has ever been observed, suggesting this process is either highly unlikely or strange stars are incredibly rare and stable. So how could we possibly tell the difference between a neutron star and a strange star from thousands of light years away? The answer lies in their fundamental properties. A strange star would be far more compact and rigid than a neutron star of the same mass. Imagine squeezing two balls of clay to the same weight. One is soft and deforms easily, while the other is hard as rock. The hard ball will be smaller. By carefully measuring both the mass and the radius of a pulsar, astronomers could see if it fits the squishier profile of a neutron star or the smaller, stiffer profile of a strange star. Another clue comes from how they cool. A neutron star cools primarily by emitting neutrinos from its dense core, a process that takes millions of years. But a strange star with its direct access to free quarks could cool much faster, like a hot piece of metal plunged into water versus one left to cool in air. Detecting a pulsar that cools suspiciously quickly could be the first solid evidence that we are looking at something far stranger than a neutron star. This search pushes our instruments to their absolute limits, a high-stakes hunt for the ultimate state of matter hidden within the corpses of dead suns. While we map the afterglow of the Big Bang, an even older cosmic fossil permeates every inch of space. Billions of these ghostly particles are passing through your body at this very moment, a silent echo from the universe's first second of existence. This is the cosmic neutrino background. It formed when the cosmos was just 1 second old, a seething, dense plasma of fundamental particles. As the universe expanded and cooled, a critical threshold was crossed, allowing these neutrinos to decouple from the primordial soup and stream freely across the cosmos, a moment frozen in time long before the first atoms ever formed. These relic neutrinos are impossibly elusive. They carry no electric charge, and their interaction with normal matter is so extraordinarily feeble that a neutrino could pass through a light year of solid lead without a single collision. This makes them the ultimate cosmic ghosts, a whisper of a signal from the dawn of everything. Yet their collective presence holds profound power, shaping the formation of the largest structures in the universe through their subtle gravitational influence. Capturing them directly is a monumental challenge that pushes the limits of our technology. Current efforts focus on indirect evidence, such as studying subtle imprints they left on the later cosmic microwave background and the distribution of galaxies. But the ultimate goal is a direct detection. Successfully measuring this ancient neutrino bath would not just be a technical triumph. It would tear open a curtain on an epoch we can currently only theorize about, allowing us to peer into the universe's fiery infancy at energies and temperatures far beyond what the cosmic microwave background can show us. It would be like hearing the universe's first heartbeat, a rhythm from a time before time itself had settled into its familiar flow. That faint whisper from the dawn of time is joined by a far deeper rumble, a vibration that shakes the very fabric of space itself. We have moved beyond light, beyond particles, to sense the universe through its gravitational heartbeat. This is the gravitational wave background, a constant, low-frequency hum that permeates all of existence. It is not a single sound, but a chorus, a cacophony of countless cosmic events overlapping into a steady, stochastic drone. Imagine standing in a stadium filled with 1 million people, all whispering at once. You cannot make out any single conversation, but you hear the collective murmur as a unified sound. The gravitational wave background is that murmur for the cosmos. Its sources are the most titanic collisions in the universe, the mergers of supermassive black holes that lie at the center of galaxies. Throughout cosmic history, as galaxies have cannibalized each other, their central black holes have spiraled together and merged, each event sending a powerful ripple through space-time. These ripples, from billions of such mergers across billions of years, combine to form this perpetual, universe-filling hum. We are on the verge of tuning into this cosmic frequency using a celestial instrument of breathtaking precision, a pulsar timing array. Projects like Nanograv use radio telescopes to monitor a network of rapidly spinning neutron stars, known as millisecond pulsars. These pulsars are nature's most perfect metronomes, beaming out radio waves with a regularity that rivals atomic clocks. As a gravitational wave passes between us and one of these pulsars, it minutely stretches and compresses the space in between, causing the pulse to arrive at Earth just a fraction of a second early or late. By carefully monitoring the subtle, correlated timing deviations across an entire array of these pulsars spread across the sky, astronomers can detect the signature of these long wavelength gravitational waves washing over our galaxy. This is not about hearing one single crash, but sensing the ocean in which we float. Detecting this background would be a revolution in perception. It would open an entirely new window onto the universe, allowing us to study the population and merger history of the most massive objects in existence, the supermassive black holes, in a way that light can never reveal. We could listen to the ghostly echoes of galactic empires merging in the dark, a history written not in light but in the quiet vibrations of space-time. The vacuum of space is not the serene, empty stage we imagine it to be. If we could peer down to the very smallest possible scale, a distance so tiny it is a decimal point followed by 34 zeros and then a 1, we would find a universe in chaos. This is the Planck length, the fundamental pixel size of reality. Here, the smooth canvas of spacetime predicted by Einstein's general relativity shatters into a seething, turbulent frenzy known as quantum foam. In this bizarre subatomic realm, the very concepts of here and there, before and after, lose all meaning. Empty space is a constantly boiling sea of virtual particles and miniature, fleeting wormholes bubbling in and out of existence in a time span too short to measure. The fabric of the cosmos is not smooth, but more like the froth on a turbulent ocean, with the geometry of space-time fluctuating wildly at every single point. This foamy nature of reality, if it exists, has profound implications. It suggests that at its most fundamental level, the universe is probabilistic and grainy, not continuous and deterministic. The challenge, of course, is that we can never directly observe this scale. The Planck length is so impossibly small that a single proton is a colossal universe in comparison. Our most powerful particle accelerators are like trying to map the fine texture of a beach with a satellite image. So how could we ever hope to find evidence for this cosmic froth? The answer may come from across the universe. When a distant gamma-ray burst explodes, it sends a torrent of the highest energy photons racing toward us across billions of light-years. If spacetime is truly a quantum foam, these photons should not all travel at exactly the same speed. The bumpy, foamy texture of space would cause subtle delays, with higher energy photons interacting slightly more with the foam and arriving a fraction of a second later than their lower energy counterparts. It would be a staggeringly small effect, like detecting a single grain of sand slowing down a tsunami. But over cosmic distances, these tiny delays could accumulate into a detectable signal. Astronomers are now sifting through the light from these ancient cataclysms, searching for this telltale signature. Finding it would be a revolution, proving that the very stage upon which the universe plays out is as dynamic and unpredictable as the actors upon it. The search for life cannot be confined to a single planet. It expands to encompass the entire architecture of a galaxy, revealing a hidden geography of habitability. Not all neighborhoods in a spiral galaxy like our own are created equal. There exists a theoretical band, a galactic habitable zone where the conditions for complex life are just right. This is not merely about a planet being in its star's Goldilocks zone for liquid water. It is about the planet's position within the grand stellar city. Too close to the bustling galactic center, and a world would be bathed in lethal radiation from the supermassive black hole and densely packed stars. The frequent, cataclysmic supernova in those crowded districts would routinely sterilize any emerging biospheres. Yet, venturing too far out into the quiet, galactic suburbs presents another problem. The stars in these remote spiral arms are ancient population II stars, formed when the universe was still young and pristine. They contain very few heavy elements, the metals forged in the hearts of earlier stellar generations. Without these elements, you cannot form rocky planets like Earth, nor the complex chemistry that life requires. The sweet spot, the galactic habitable zone, is a narrow ring between these two extremes. It is a region with a rich supply of heavy elements for planet building, but far enough from the chaotic core to avoid constant bombardment. Our solar system orbits in just such a zone, about halfway out from the Milky Way's center. Is our location here a mere happy accident, a single winning ticket in a cosmic lottery? Or is it a subtle clue that intelligence, wherever it arises, is a phenomenon dependent on this specific galactic address? The answer shapes our expectations for the entire cosmos. If the galactic habitable zone is a strict prerequisite, then the number of potential civilizations plummets, confined to a thin, celestial band of real estate. Our solitude becomes more understandable, but if life is more tenacious, capable of flourishing in the galactic core or the metal poor fringe, then the universe could be a far noisier and far stranger place than we ever dreamed. The ultimate expression of a civilization's power might not be a signal, but a silent, star-sized machine. A Dyson sphere is a hypothetical megastructure, a vast constellation of energy collectors built by a species so advanced it has learned to harness the total output of its sun. Imagine a swarm of satellites or a solid shell completely enveloping the star, capturing every single photon of light it emits. Such a civilization would no longer be planet-bound. It would operate on a stellar scale, its energy needs so vast that only the power of an entire star could suffice. For us, searching for these cosmic power plants means looking for a specific, telltale signature. A star cloaked by a Dyson sphere would present a bizarre contradiction. In visible light, it would be dim or even completely dark because the structure is blocking the starlight. But all that captured energy has to go somewhere. The laws of thermodynamics are unforgiving. The megastructure would absorb the immense energy, and like any machine, it would eventually radiate that energy back out as waste heat, glowing brightly in the infrared part of the spectrum. So astronomers search the skies for stars that are anomalously bright in infrared, stars that seem to be radiating far more heat than they should for their visible brightness. This is where a star like KIC 8462852, Tabby's star, captured worldwide attention. Its bizarre, deep, and irregular dimming initially sparked the thrilling idea that we might be seeing the construction of a Dyson sphere, with massive, irregular panels occasionally blocking our view. While further study pointed to a more natural, if strange, explanation involving immense clouds of dust, the episode highlighted a profound shift in our search for intelligence. We are no longer just listening for a message. We are scanning the galaxy for the ghostly thermal fingerprints of cosmic engineers, for the silent, infrared glow of a star that has been caged. No definitive evidence has been found, but the search continues, a quiet hunt for the ultimate monument to a civilization that has learned to build with suns. The two most successful theories in all of physics are at war with each other. On one side, you have Einstein's general relativity, a masterpiece that describes the cosmos on its grandest stages. It tells us how planets orbit, how galaxies cluster, and how the very fabric of space-time curves around massive objects. It is the theory of the immense, the beautiful geometry of gravity. On the other side, you have quantum mechanics, the bizarre and counterintuitive rules that govern the atomic and subatomic world. It describes a reality of probabilities where particles can be in two places at once and are connected by spooky action at a distance. It is the theory of the infinitesimally small, and it works with stunning precision. The problem is, these two rule books are written in completely different languages. When you try to apply the smooth, geometric rules of relativity to the fuzzy, probabilistic world of the quantum, the math breaks down into nonsense. This is the quantum gravity conundrum, the single greatest unsolved problem in theoretical physics. We desperately need a single theory that can unite them, a theory of quantum gravity. Without it, our understanding of the universe is fundamentally incomplete. We hit a wall whenever we try to peer into the two most extreme environments nature has to offer. The first is the very center of a black hole, the singularity. General relativity predicts that all the matter that falls in is crushed into an infinitely dense, infinitely small point. But infinity is a sign that our physics has failed. Quantum mechanics should step in to describe that point, but its rules are incompatible. The second is the moment of the Big Bang itself, when the entire universe was compressed into a speck smaller than an atom. What were the laws of physics in that first fleeting instant? Our current theories simply cannot say. To answer these ultimate questions, scientists have proposed some of the most mind-bending ideas in human history. The most famous is string theory, which suggests that the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating strings or membranes. The different vibrations of these strings, like the notes on a violin, produce all the different particles and forces we see. In this theory, gravity emerges naturally from the symphony of strings. The other major contender is loop quantum gravity. It takes a different approach, suggesting that space itself is not a smooth continuum, but is woven from a fabric of tiny, finite loops. Picture the universe as a vast, cosmic tapestry where space is composed of individual threads. This quantized space prevents the infinities of the singularity, meaning the Big Bang might not have been a true beginning, but a great bounce from a previous universe. The challenge with both of these ideas and others like them is almost insurmountable. How do you test them? The energies required to see these effects are a quadrillion times greater than what our most powerful particle colliders can produce. The scales involved are a billion times smaller than a proton. For now, these theories remain beautiful pieces of mathematics, waiting for a cosmic event or a stroke of genius to reveal a crack in reality through which we can glimpse the truth. Every force we have encountered so far has its limits, but what if the driving engine of cosmic expansion has no ceiling at all? This is the terrifying potential of phantom energy, a hypothetical and extreme form of dark energy that turns our current cosmic fate from a slow freeze into a definitive, shattering cataclysm. In our standard model, dark energy is a constant, its repulsive force steady and unwavering as it pushes galaxies apart, but phantom energy is different. It is dark energy with a twist of nightmare logic. In this model, the energy density of dark energy does not stay the same, it grows. It amplifies itself over time, becoming stronger and more potent as the universe expands. This creates a runaway feedback loop with truly apocalyptic consequences. The acceleration of the universe would not just continue, it would exponentially increase, rocketing toward an infinite value in a finite amount of time. The ultimate destination of this path is known as the Big Rip. Imagine the repulsive force growing so powerful that it first overcomes the gravitational glue holding clusters of galaxies together. These vast cities of stars would be flung into the deepening void, their cosmic communities torn asunder. But the destruction would not stop there. As the phantom energy continues to intensify, it would next target individual galaxies. The Milky Way, Andromeda, every beautiful spiral and elliptical would be shredded, their stars scattered like dust in a hurricane. The horror would then come for our own solar system. The phantom force would overwhelm the sun's gravity, and Earth would be ripped from its orbit, cast alone into an ever-accelerating darkness. Still, the phantom energy grows. Next, the force would tear the planets and the sun themselves apart. Then it would target Earth. The gravitational and electromagnetic forces that hold our world together would be defeated, and the planet would explode into a cloud of primordial atoms. Finally, in the last fleeting moments before the end of time itself, the phantom energy would perform its most gruesome act. It would tear apart the very fabric of atoms, ripping electrons from their nuclei, and then shred the nuclei into their constituent quarks. Every single piece of matter in the universe would be reduced to a chaotic, disconnected spray of fundamental particles, unable to ever interact again. The cosmos would not just grow cold and dark, it would cease to have any structure whatsoever. It would become a formless, expanding nothingness. Current estimates, based on our observations of the universe's current acceleration, suggest that if phantom energy is real, this entire catastrophic sequence could play out in as little as 22 billion years from now. While this is an almost unimaginably long time, it is a definitive end, a violent and absolute conclusion to the cosmic story. The phantom energy threat remains speculative, a dark possibility on the furthest edge of cosmology. Yet its very conception forces us to confront a profound question. Is the force that dominates our universe a gentle, constant pressure, or is it a gathering storm, one that will ultimately unravel the very threads of reality itself? Deep within the theoretical heart of a black hole lies a point of infinite density, a singularity where the known laws of physics cease to exist. General relativity tells us this monstrous point is always hidden, forever veiled by the event horizon, the point of no return from which not even light can escape. But what if that cosmic curtain were torn away? The brilliant physicist Roger Penrose proposed a startling answer to this terrifying possibility, a concept known as the cosmic censorship hypothesis. It is a profound conjecture that nature itself abhors a naked singularity. The universe, according to this idea, possesses a fundamental modesty, always ensuring that every singularity is discreetly dressed behind an event horizon, protecting the rest of reality from its infinite chaos. The problem is that Einstein's equations, in their pure mathematical form, do not actually forbid a naked singularity. They allow for the possibility of these ultimate cosmic monsters to exist exposed, their infinite gravitational fury laid bare for the universe to see. Without the protective shield of an event horizon, the influence of a naked singularity would be unleashed. The predictable, causal flow of the universe would shatter. Cause and effect would become meaningless. Physics, as a science of prediction, would become impossible, as the unfathomable laws at the singularity could send unpredictable influences rippling out across space and time. So is cosmic censorship a fundamental, unbreakable law of the cosmos, or is it a rule that can be broken? Scientists have long searched for theoretical backdoors, scenarios where a naked singularity might be forged. Could one be created in the aftermath of a hyper-energetic collision between particles or black holes, a fleeting tear in the fabric of spacetime before it quickly heals itself? Or might certain exotic forms of gravitational collapse, involving perfectly symmetrical or rapidly rotating stars, lead to a singularity without first forming a protective horizon? If such an event were ever observed, even for an instant, it would be a revolution. The veil would be lifted and we would be granted a direct glimpse into the quantum heart of gravity, a place where space-time itself is torn apart. It would force us to rewrite our understanding of reality, revealing the true, unvarnished face of the universe's most extreme birth. The idea of a single universe may be a profound illusion. The concept of the multiverse suggests our cosmos is just one page in an infinite cosmic library, and scientists have systematically categorized this staggering possibility into distinct levels. Level 1 is the simplest to grasp, born from the sheer scale of our own reality. If the universe is truly infinite and the matter within it is finite, then every possible arrangement of that matter must repeat. Somewhere in the vastness beyond our cosmic horizon, there is an identical copy of you reading an identical copy of this script. There is a world where dinosaurs never went extinct, and another where every coin you ever flipped landed on heads. This is not a separate realm, but a direct consequence of infinity within our own cosmic bubble. The implications are humbling, suggesting that everything physically possible is not just probable, but inevitable, somewhere in the unobservable reaches of our own universe. Yet this leads directly to a more radical concept, Level 2. This is the inflationary multiverse, born from the theory of cosmic inflation. Our entire observable universe may be just one bubble in a frothing, eternal sea of spacetime. In this eternal inflation, new bubble universes are constantly budding off from the inflating background, each one a self-contained cosmos with its own Big Bang. Crucially, when these bubbles form, the fundamental constants of physics, like the strength of gravity or the mass of an electron, can be randomly set to different values. In most of these bubbles, the constants would be inhospitable to life. Atoms might not hold together, or stars might never form. We find ourselves in a bubble where the numbers are just right, not because of design, but because we could not exist in any of the others. This is the ultimate anthropic selection. Then there is Level 3, which emerges from the quantum realm. The many worlds interpretation of quantum mechanics proposes that every time a quantum event has multiple possible outcomes, the universe does not choose one. Instead, it splits, branching into a new timeline for every possibility. In this view, a particle is not in a superposition of states. It is in all states, each in its own newly minted universe. The moment you read this sentence, a universe split off where you decided to stop watching. Another split when a radioactive atom in a distant star decayed a microsecond earlier or later. The branching is constant and infinite, creating a mind-bogglingly vast tree of parallel realities, all equally real, diverging from every quantum decision ever made. The philosophical weight of these ideas is immense. They challenge our very definition of reality and our place within it. But are they science or just metaphysics? The central problem is testability. How can we ever observe another universe if, by definition, it is beyond our causal reach? For the Level 1 multiverse, we cannot see beyond our cosmic horizon. For Level 2, other bubbles are in entirely disconnected regions of spacetime. For Level 3, the branching worlds are forever inaccessible. Some physicists, however, are searching for indirect evidence. A violent collision between our bubble universe and another in the distant past could have left a bruise on the cosmic microwave background, a strange pattern of hot or cold spots that defies conventional explanation. Others look for subtle imprints in the gravitational wave background. For now, the multiverse remains a powerful, provocative framework, a shadow on the cave wall of our knowledge, forcing us to ask if the ultimate nature of reality is not a single story, but every story told at once. This paradox forces us to question the very foundation of our memories and experiences. Our universe appears incredibly ordered, a system that has moved from a state of high energy and uniformity to one of complex structures like galaxies, planets, and life. This seems to violate the second law of thermodynamics, which states that the universe as a whole is constantly moving toward a state of maximum disorder or entropy. In the late 19th century, physicist Ludwig Boltzmann proposed a way to reconcile this. He suggested that our ordered cosmos is not the norm, but a rare and temporary statistical fluctuation within a much larger, chaotic, and high-entropy universe. In an eternal or infinite cosmos, every possible arrangement of particles, no matter how unlikely, will eventually occur by pure chance. A fully formed, self-aware brain could spontaneously assemble from the void, complete with false memories of a past that never happened and sensory impressions of a world that does not exist. This is the Boltzmann brain. The chilling paradox emerges when we apply probability. In an eternally expanding universe dominated by dark energy, space becomes an increasingly cold and empty void. Over an infinite amount of time, the number of such random, conscious fluctuations would vastly outnumber the number of ordered universes that evolved naturally from a low entropy beginning like the Big Bang. Statistically, you are far more likely to be a lone, disembodied brain that just popped into existence a moment ago than a person with a real, continuous history in a stable universe. So which is more probable, that the entire ordered cosmos we see around us is real, or that you are a fleeting accident, a momentary glitch in an otherwise silent and chaotic eternity? The Boltzmann brain is not a serious proposal that we are all illusions. Instead, it is a profound warning sign that our current cosmological models might be incomplete or fundamentally wrong. It highlights a deep problem with the initial conditions of our universe. Why did the cosmos start in such an incredibly ordered, low-entropy state, a preposterously unlikely starting point that allowed for everything that followed? The search for an answer to that question may be the only way to silence the unsettling whisper from the void. This unsettling possibility forces us to confront the very nature of our reality. The simulation hypothesis is not science fiction, but a serious philosophical argument that our universe and everything in it might be an elaborate digital construct. The logic popularized by thinkers like Nick Bostrom follows a stark chain of reasoning. First, assume that at least one civilization in the universe's history reaches a post-human stage, a level of technological maturity so advanced it can generate conscious, detailed simulations of its own ancestors. Second, assume that such a civilization would have any interest in running these simulations, perhaps for research or entertainment. If both these conditions are met, the numbers become overwhelming. A single advanced civilization could run billions, even trillions of these simulations. If that is the case, then the vast majority of all conscious minds that have ever experienced a world would not be base reality beings, but simulated minds living inside a computer. Statistically, the odds that you are one of the original biological entities are astronomically small. We are far more likely to be living in one of the countless simulations. This idea resonates with the digital worlds we are already building. Our own video games are evolving from simple pixels to vast, immersive universes with their own physics and ecosystems. Given a few more centuries or millennia of technological progress, the line between a simulated reality and a base reality could become completely indistinguishable to those inside it. So how could we ever know? Some scientists have proposed looking for potential glitches in our own universe, subtle errors in the code. Perhaps we might find a fundamental limit to resolution at the smallest scales, a pixelation of spacetime. Or maybe the constants of nature, which seem so finely tuned, are actually just fixed parameters in the simulation's programming. Others argue the hypothesis is fundamentally untestable and therefore unscientific. Even if we found such a glitch, it could simply be a deeper law of physics we do not yet understand, not proof of a programmer. The true weight of the simulation argument is not in proving it true, but in the profound philosophical shift it demands. It reframes our entire existence, turning the cosmos from a physical place into a potential narrative, a story being run on some unfathomable hardware in a reality we can never access. But even the reality we take for granted is a fragile construction. The quantum world beneath our feet is a place of ghostly superpositions, where particles exist in a haze of multiple possibilities until the moment they are observed. So how does this fuzzy, probabilistic realm transform into the solid, predictable world of our everyday experience? A compelling answer is emerging from a theory known as quantum Darwinism. It suggests that the universe itself has a form of natural selection, not for life, but for states of reality. In the quantum arena, countless potential states compete, but only the fittest survive to become what we call objective facts. The key to this fitness is not strength, but sturdiness and the ability to be copied. When a quantum system interacts with its environment, be it a stray photon, a dust particle, or the air around it, it leaves imprints. Most quantum states are fragile and delicate, collapsing into randomness when they touch the world. But a select few are robust. These resilient states can be repeatedly measured and copied without being destroyed, spreading their information into the environment like a virus. Think of a stone in a river. The water flows around it, and countless droplets splash off its surface, each one carrying a tiny piece of information about the stone's position and shape. You do not need to touch the stone to know it is there. You just need to sample the water. In the same way, the classical properties we observe, like the position of a chair or the momentum of a baseball, are not special because we look at them. They are special because they have been broadcast, copied, and replicated into the environment trillions upon trillions of times. This widespread information makes them objective. What you see and what I see agrees, not because of a shared consciousness, but because we are both accessing the same widely disseminated data. The chair is objectively there because its quantum state has been so thoroughly bred into the light bouncing off it, the air molecules hitting it, and the gravitational field anchoring it. Quantum Darwinism paints a picture of a world where reality is not decreed, but emerges through a democratic process of information sharing. The universe, in its constant interactions, votes on what is real, and the winners are the states that can withstand the scrutiny of being known. The universe's most profound secrets might not lie within its depths, but on its skin. A radical idea known as the holographic principle proposes that all the information describing everything inside a volume of space, every star, every planet, every one of us, is not contained within that volume at all. Instead, it is encoded on its outer boundary like a cosmic hologram. This theory did not emerge from pure speculation, but from the fiery logic of black hole thermodynamics. When matter falls into a black hole, it seems to vanish, but its information, the quantum blueprint of what it was, cannot be truly destroyed. The holographic principle resolves this by suggesting the information is not lost inside, but is smeared and stored on the black hole's event horizon, the two-dimensional surface that marks the point of no return. The surface area of this horizon, not the volume it encloses, dictates the maximum amount of information the black hole can hold. This stunning revelation was then extended to the cosmos itself. If a black hole's interior can be described by a theory on its boundary, perhaps our entire three-dimensional universe with all its rich complexity is similarly a projection. We may be living inside a vast hologram, a three-dimensional movie whose source code is written on a distant, two-dimensional surface at the edge of everything we can see. Your perception of depth, of solidity, of moving through a world of volume would then be an exquisite illusion, a translation of data from a flat screen. The implications shatter our classical intuition. It suggests that space-time itself is not fundamental but emergent, a secondary effect that arises from a deeper, more information-theoretic reality. This principle offers a potential path to unify the two great pillars of physics, general relativity and quantum mechanics, by redefining the very stage upon which they perform. If true, the holographic principle means the universe is fundamentally simpler than it appears, that all the forces, particles, and dimensions we experience are the rendered output of a grand, two-dimensional computation happening at the limits of perception. The grand cosmic story, from the first spark to the sprawling web of galaxies, must eventually reach its final chapter. The ultimate fate of everything, from the largest supercluster to the smallest atom, hinges entirely on the true nature of the mysterious force we call dark energy. One prevailing vision of the end is known as the heat death or the big freeze. In this future, dark energy continues its work as a constant, gentle pressure. The acceleration of the universe never ceases, pulling all galaxies away from one another until every star in the night sky, except those in our own merged Milky Way Andromeda galaxy, fades from view entirely. Over trillions of years, the last stars will exhaust their fuel and burn out. Black holes will slowly evaporate via Hawking radiation. The universe will approach a state of absolute maximum entropy, a final equilibrium where the temperature everywhere nears absolute zero. It becomes a thin, ever-expanding sea of isolated particles and radiation, a dark, cold, and silent graveyard where no new structure can ever form again. But what if dark energy is not so gentle? Another, more violent destiny awaits if the phantom energy hypothesis is correct. This is the Big Rip. In this terrifying scenario, the energy density of dark energy does not remain constant but grows stronger over time. The acceleration becomes exponential, a runaway force that eventually overwhelms every binding force in the universe. First, galaxy clusters are torn apart. Then, individual galaxies are shredded. The phantom force would rip stars from their orbits, tear planets apart, and finally, in the last fleeting moments, rip apart atoms, nuclei, and the very fabric of spacetime itself. The universe would end not with a whimper, but with a definitive, catastrophic unraveling of reality. There remains a third, cyclical possibility, the Big Crunch and the potential for a big bounce. This scenario requires that dark energy weakens or reverses, allowing the collective gravity of all matter to finally halt and reverse the cosmic expansion. Galaxies would begin rushing back toward one another, space itself contracting. The temperature of the cosmos would rise as everything is compressed into an increasingly smaller, hotter, and denser state. The universe would end in a fiery inferno, collapsing back into a singularity similar to the one from which it was born. And in some theoretical models, this singularity does not mark a final end but a rebirth. The universe could bounce, triggering a new Big Bang and birthing a brand new cosmos from the ashes of the old. This cyclical model offers a vision of an eternal, breathing universe with no true beginning and no final end. Our current observations point toward the continued acceleration of the Big Freeze, but the truth is, the final verdict is not yet in. The ultimate fate of all existence remains an open question, one of the greatest in all of science. It depends entirely on the precise properties of dark energy, a force that makes up the majority of the cosmos and yet remains almost completely unknown to us. The final chapter of our universe is a story we are still learning to read, written in the invisible ink of a cosmic mystery. 50 galactic wonders have unfolded before us, a journey from the immense gravitational pull of the great attractor to the subatomic froth of quantum foam. We have seen how dark energy dictates our cosmic fate and how spooky quantum connections hint at a deeply interwoven reality. Each of these phenomena, from the silent majesty of Hoag's object to the frantic bursts of magnetars, stands as a monument to our ignorance. They are not merely unanswered questions, but blazing signposts pointing toward vast, uncharted territories of physics. Our current understanding of the universe, for all its sophistication, is likely a primitive sketch, a child's first drawing of a boundless and infinitely complex masterpiece. So the next time you find yourself beneath a clear night sky, remember this journey. See not just the pinpricks of light, but the invisible dark matter weaving them together. Feel not just the emptiness, but the phantom energy that may one day tear it all apart. Let the profound mysteries we have explored rekindle your innate sense of wonder. Stay curious, for the cosmos is far stranger and more magnificent than we have yet dared to dream. If this voyage into the unknown has captivated you, subscribe for more deep dives into the universe's greatest secrets. And we would love to know which of these 50 phenomena left you the most baffled. Share your thoughts in the comments below.